Welcome to this introduction on waves as it relates to the Physics 110 lab on standing waves. So we'd like to start by discussing what a wave is and how to describe waves, and we will lead into some of the phenomena that is associated with waves, in particular sound waves. So this week we are going to attempt to measure the wavelength and velocity of sound waves that are created in a tube. So we'll have an open-ended tube, and then we'll have a tube that's closed at one end, and we will use tuning forks to create the waves and try to find the resonant points within the wave. So I'd like to explain what all of that means, and we'll start with the definitions of waves. So a wave is anything that whenever you disturb something, could be any type of medium. So for example, you could have water or string or a spring. There are also types of waves that do not require mediums. That would be a disturbance that would be created in electric and magnetic fields, and that is actually what creates light. So we're going to stick to the mechanical types of waves that require a medium in our discussion today. And so a couple of examples of that, you may see something such as a water wave. So in this particular image, you see a ripple that's created in water when a drop of water hits the surface and disturbs that surface. So a formal definition of waves would be periodic disturbance that transfers energy. And if you think back to last week, an earlier lab where we did simple harmonic motion, you'll recall that we had a mass on a spring, and we would disturb that by pulling the mass slightly down or compressing it slightly up on the spring, and then allowing it to oscillate. And if you have an oscillation such as that, if you imagine here looking at this animation, you'll see the blue dot that's oscillating up and down. That could represent the mass that was on a spring. And you'll see that we could model that with a wave that looks like a sine wave. So when we talk about waves, there are also types of waves that refer to the way they move through the medium. So for example, if we look at this image here, we have both longitudinal and transverse waves. So the type of wave that you typically think of, that's the way they're described when I showed you earlier with the sine wave, that would be this wave here that you see in blue. And this is known as a transverse wave. Transverse waves are waves that move perpendicular to the direction of travel, whereas a longitudinal wave moves parallel. So the orange you see here is a longitudinal wave. And you'll notice when I press run here on this animation, you'll see that these areas of where the lines are compressed together would be related to the tallest part of this wave, and where they're stretched apart would be the low part of the wave. So there are different parts of the waves that we need to talk about in order to be able to describe waves. One of the major ones is going to be the amplitude, which refers to the height of the wave. So you can see that I can adjust the amplitude here by making it smaller, or I can make it higher. So in the case of sound waves, a taller wave or a larger amplitude would create a louder sound. Another major component of waves is what's known as the wavelength. One easy way to measure a wavelength would be from peak to peak, as you see here. But also you could measure it from where it crosses the line, not to the next point here, that would only make half a wavelength in this case, but you would go to where the wave repeats itself. So in other words, you notice it's a downward slope here. So if I measured from this point over to this point, then this would be where it's making a downward trajectory again. So in other words, you're completing one cycle. Another thing would be the velocity of the wave, the speed at which it moves. So if we go back to the lab manual, you'll notice here that they're showing a wave moving to the left, and they're describing the velocity here with a velocity vector. One other important thing that's related to is something called the frequency. So one way to think about the frequency is to think of the number of wavelengths that are passing by a point in a given amount of time. So typically you would measure this in seconds. So frequency is typically given in terms of hertz, which means number of cycles per second, or specifically for waves, usually you're talking about the number of wavelengths per second. And so if you pick this point here, maybe the starting point, then the number of wavelengths that would pass by in a second would tell you what the frequency would be. So you'll notice if I increase the frequency here, you'll see that I have more wavelengths passing by in the given amount of time. Now in this particular animation, the velocity stays constant. So if I increase the frequency here, the wavelength becomes shorter. So there's a relationship between these two mathematically. And if we go back to the lab manual, you'll notice here that we have velocity is equal to lambda times f. So v is the velocity, f is the frequency, and lambda is the wavelength. All right, so now that we've defined some of the parts of a wave, and we've talked about how these waves would move along, if we were to think about more than one wave, we can talk about what's known as superposition waves or wave interference. So we'll stick to the transverse waves for now because it's easier to visualize. So imagine if we had two waves that are moving in the same direction. So if I begin this animation, we'll see that they're both moving to the left. You've got the red wave and a blue wave. And when they are what's known as in phase, or in other words lined up, so peak to peak and trough to trough, so to speak, you'll see that you would add those two waves together. So in other words, if I put them both in the same plane here, add those two together, then you'll see that these two amplitudes here would add to give a much larger amplitude. Now if I slide this so that one of these waves is not lining up with the wave above it, in other words more out of phase, you'll see that the amplitude begins to go smaller until the point I reach where I'm completely out of phase. In other words, a peak of this wave would match the trough of that wave. And so effectively, if they're the same amplitude, then they would cancel each other out. If we wanted to look at differing wavelengths, but also more importantly in this case, are two waves traveling in opposite directions. So in this case, if I were to run the red wavelength to the left and the blue one to the right, you'll notice that when I add them together, I get a very complex waveform here. And this is because I have the blue wavelength that's longer than the red. And if you were to lay these over top of one another, it makes it a little bit easier to visualize. And you'll see that maybe as these two peaks line up, you get the largest amplitudes. And at points where they are exact opposite, then they cancel out so that they would be more flat, as we saw earlier. Now, if I make both of these wavelengths the same length, and they are still running in opposite directions to one another, you'll notice now, so if I have them both being the same length of wave, so the same wavelength, then at this point, as they pass one another, you're creating what's known as a standing wave. So I'll try to pause this. You'll see at this point they're pretty close to having these two lined up so that you get close to a maximum amplitude. The place where you have this maximum amplitude, either positive or negative, is known as an antinode. You'll notice that it continually moves. So if I can continue to run this, you'll see that the green dots here are representing what's known as an antinode. And that's the point where we have the maximum amplitude that's created once they are in phase with one another. But there are, what's unique to a standing wave is there are points that as these two pass each other, and it's a little easier if I lay them on top, there is a point where the waves consistently cancel each other out as they pass, and these are known as nodes. Because we're talking about sound waves, they're technically going to be longitudinal waves, or we're going to be creating also sometimes referred to as pressure waves. One way that you can see this is if you were to take a slinky, compress that slinky longitudinally, you can see the longitudinal waves. So I'll play this, and you'll notice that you can see that wave, the compression travel down the wave there, so it gives you a visual of what a longitudinal wave can look like. I'll start first looking down at this lower section where we have a closed end of the tube. And what they're trying to draw here is the wave section, but as it oscillates up and down, they're trying to show you transverse interpretation of this wave. And you'll notice that the antinode would be the points where you're seeing maximum amplitude here. So if you want to get resonance in a tube, you're going to have the wave go down and bounce, reflect off the closed end of the tube and come back. And so if you find the right length of this tube for a particular frequency or a particular wavelength, then you will be able to get the antinode to line up with the opening of the tube, and you'll create the loudest sound. And so you'll see that in the lab procedural video. So there are a few different ways you could do this. You could have it so that the tube is long enough for a particular frequency, such that you're always going to have a node here. One way to think about this is if you're thinking about the pressure waves, a longitudinal wave going through here, the air molecules are being oscillated back and forth. Well, when they hit the side of this tube to reflect, they can't really move anywhere. So that's one way to kind of think about this as being a node, so that the air molecules are not oscillating back and forth. But over at this end, they would be freer to move about. You could create a longer tube such that for a particular wavelength where you still have the node at the closed end, but you could create another node here and have an opening at this end. All right. And so then you could create again 2 nodes within the tube and still have an antinode at the opening over here. This would be known as harmonics when you find these locations. So there's only going to be exact lengths of tube for a particular wavelength that will create these different harmonics. And if you go to an open-ended tube, so it's open on both ends, you have a similar phenomenon that happens in terms of the reflections. But in this case, because it's open at both ends, you would have the antinodes at both of the open ends, and a node would reside somewhere inside the tube. So if you had a different length tube or a different wavelength, you could create 2 different nodes here, and then of course you see 3, and you could continue to create even more nodes on the inside. Just as long as you have the antinodes that line up on the ends, you'll still have your resonant points. Looking at this in an animation, if I have an open-ended air column, then the first harmonic would look something like this. Okay, and so that it's oscillating back and forth. And you'll notice the points here in the middle where it's being compressed. You'll be able to take a look at the pressure itself. This gives you an idea of what the pressure would be. You'd have the highest pressure here in the middle where the node would actually be. So you notice here in the center, if you have a standing wave, you're going to have antinodes at the end, and you would have a node here in the middle for the first harmonic. If I go to the second, that's where I'm placing 2 nodes on the inside, but I still have my antinodes at the end. So I'll remove this transverse wave for a moment so that you get an idea of what the longitudinal wave looks like without our transverse representation. So let's go to the third harmonic, and I'll show the transverse wave here so you can see that the nodes correspond to the points where it either is compressed the most or stretched out the most here. Okay, so let's now move to the closed end air column, so that on the left we have a closed end, and the first harmonic would look like this, so that your transverse wave would show you where the node is here. If we go to the next harmonic, which technically is the third harmonic here because we can only have odd numbered for the closed end because we have to have a node fixed here. And you would have your second node here and the opening at this end. Okay, and then of course we could have 2 nodes on the inside and still have our antinode here. The next thing I want to point out about this is about the length. So you notice here at this first one we have a quarter wavelength, but when I go to having 2 nodes, I'm at 3/4 of a wavelength. And if we go back to the open-ended air column, in this case, the first harmonic is half a wavelength. So let's compare the two. In this one, it was quarter of a wavelength. Here it's half of a wavelength. Okay, so we can pause this And we'll see that if I were to draw the wave, I would be starting at a trough going up to a peak in this case. Whereas for the first harmonic of the closed-ended tube, and I'll try to stop this end, you'll notice here that it's only a quarter. We're starting here at this point, working our way up. So if I go to, let's say, the third, here you'll see that we've made it halfway through a wave and then 1/4 of the next, so that's 3/4 of a wavelength. Then going back to the open-ended air column again, you'll see that we've started here at a trough, we go up to a peak, and then we're back down to a trough again. So at this point we have one complete wavelength. Whereas if I went to the the third harmonic here, you would then see 1.5 wavelengths. So you notice we're making half wavelength steps here. Okay, so as this relates to our lab, we are going to have on our particular tubes with the tuning forks that we're going to use to excite the air on the inside of the column, you're only going to be able to find the first harmonic for the open-ended air column, and you will find what's known as the third harmonic for this one. So in other words, for the open-ended air column, the harmonic you'll find is this one. So whenever we measure the length of the tube from here to here, we would have to multiply by 2 in order to find our entire wavelength. Okay, and at that point, we could go back to the lab manual and use this simple equation here to plug in the frequency. The frequency is going to be known because it'll be stamped on our tuning fork, and then the wavelength we'll measure directly. But the wavelength, we're only going to be able to find half, so we'll have to take the length that we measure, multiply by 2, then we can plug that in the equation along with the frequency that we know to calculate what the velocity is. And what we're going to do then is compare that velocity to what's to the known value of the speed of sound in air. So let's look back at the closed end, and the one that we're going to find there is the only length of the tube. The length of tube we have is only going to allow us to find 3/4 of a wavelength. It's not going to be short enough to find the first harmonic, and it's not going to be long enough for us to find that third mode here known as the fifth harmonic. So the last thing I want to show you is a nice animation that Dan Russell from Penn State has created, and that is showing here the longitudinal representation of the wave. But here he's showing a closed-end tube, so this is for the closed-end model that we saw earlier with this, except in this case it's closed on the right-hand side. And this gray bar is meant to represent something that's causing an oscillation, whether it be a piston that's moving the air, or in our case it's going to be a vibrating tuning fork. And these black dots represent air molecules. And so this was a nice visual representation to get an idea of what's going on inside the tube, so that you'll notice that there's a red dot here that's not moving, and this corresponds to a node for the standing wave when you imagine it as a transverse wave. Then you'll notice for the antinode, that's represented by this right red dot here that's oscillating back and forth. And so this bottom down here is just showing the air pressure. And so within the lab assignment in Canvas, I have a video of a demonstration that we have in the department that shows a flame tube known as a Rubens tube. And you're able to create higher pressure areas that will cause the flames to go higher. So I encourage you to take a look at that video once you're finished with this one. So hopefully this will help give you a good idea, a good introduction to the waves and to the wave phenomena that we're going to be looking at this week in the Standing Wave Lab.